Okay, this is the third part of relativity, and this is as far as I'm going to take you. I want to talk about this equation, E equals mc squared. This is the most famous equation in the history of science, and it is, or mathematics or anything, everybody knows E equals mc squared. Most people don't know what it means. It is called the energy mass equivalence. And this says that the energy that an object possesses is equal to mass times the speed of light squared. So that basically, if I know how much mass I have, I can actually convert that into how much energy is present and vice versa. In other words, energy and mass are related to each other by this number, or we would say that energy is congealed, mass is congealed energy, and energy is mass, which is being expressed as energy. So where did this equation come from? Well, it comes about because the speed of light is like a constant for the universe. You can't go faster than the speed of light. So you may remember, I hope you do, this equation from back in first semester. That says that if I put energy into an object, the speed will increase. That there's a measure of energy called the kinetic energy, and the faster something's going, the more kinetic energy it has. Right? Now, I'm going to do something here. I want to solve this for V. So if I move this over, this would be 2 over m ke is equal to V squared, or taking the square root of both sides. And then I'm going to separate this out. 2 over m times 1 of the square root of ke is equal to V. Now, I wish I didn't have to do this math, but you're just going to have to do your best to follow it. What I'm going to do is think of this as my y. So this is like y is equal to a constant times the square root of x. And what I'm going to do, just to make life simpler for us, I'm going to plot this as the square root of the kinetic energy. In other words, if I put in 4 joules, square root of 4 is 2, and that will give me what my velocity would be. And if we plotted these, what we would get is a straight line. And the slope of this straight line would be 2 over m, the square root. Right? So far, so good. Here's what Newton would have said. Newton would have said, if you put in 1,000,000 joules, square root of 1,000,000 is 10,000, and multiply that by 2 over the square root of the mass, and that'll tell you how fast you're going. And Einstein said that's wrong, because there is an upper limit up here called c, speed of light. You can't go past this. Now, what's going to happen is, at low velocities, like we pointed out, even up to 1/4 the speed of light or half the speed of light, you don't really notice much different. But what's going to have to happen is this is going to have to start going like this until we finally reach what we call the asymptote. In other words, I put in more and more and more and more energy, but I don't get out more and more speed. I top out at speed c. Well, I wonder what could explain that. Well, what's happening to the slope here? The slope here was 2 over m. The slope here is much less. It's a lower slope. And what Einstein realized was happening is, since V and Ke, I know this equation is right, what's happening is my mass is getting bigger. If 2 over m, if m is twice as large, this slope is half as flat. If m is 1,000 times as large, the slope is 1/100th as steep. And Einstein, this is, there's a great video called Einstein's Big Idea, And I'll talk to you about it. I may do it as extra credit for those of you who want to bring up your grade. You've actually watched a little clip of it, of Faraday discovering electromagnetism. But it goes through the whole E equals mc squared, but it really brings this into focus. When Einstein understood this, it almost took his breath away. What is happening is this. As I put in energy, I increase the mass so that the mass and the energy are linked together. And that is then where that equation comes from. The energy is mc squared. Now you say, well, where did the half go to? What's happening is that half is down here, but once we get up here, this is virtually flat. I'm not going to go into that, but I don't know if you can see it, but these are very similar equations. But the point is that when you put in energy, it converts it to mass. And as soon as Einstein saw that, he said that mass and energy are the same thing. Energy turns into mass, mass turns into energy. By the way, this is not just true at high speeds. This is true at any speed. Remember this equation that we had from before, that m is m0 over the square root of 1 minus v squared over c squared. That equation is true no matter what the velocity is. So if you're traveling down the road at 60 miles per hour, some of that speed, some of the energy that it took to get you up to that speed has gone into your body. And you are now more massive as a result. Not much more, because 60 miles an hour is such a tiny fraction of the speed of light that we would hardly ever spot that. But you can kind of see what's happening here. If I'm going along and all of a sudden I'm at 95% the speed of light, well, let me go back to this equation, F equals ma. This is Newton's famous second law. But Newton's second law actually said a change in of force equals mass times a change in velocity. In order to change the velocity, I have to add force. But that was assuming this was constant. What would happen if I wanted to keep my change in velocity the same? That's this right here. But my mass was increasing. Let's say you were driving along and pushing on something and I kept dropping blocks on it. You would have to keep pushing harder and harder. And that's what Einstein realized here. So this is called the energy mass equivalence equation. Energy congeals and becomes mass, and mass then can become energy. And by the way, that's exactly what happens in a nuclear reaction. If you take a uranium atom and you split it into two smaller pieces and you add up, you find the mass here, the mass of that, that nucleus, we'll call this nucleus 1, and this 2 and 3, and you take and add mass of 2 plus the mass of 3, the mass of 1 will be greater than the mass of 2 and the mass of 3. Well, why? Because it takes energy to hold the nucleus together. And when you split the nucleus, the energy that was needed to hold the nucleus together is now gone. And as a result, that's the explosion. As a result, that energy has been released, and the two particles here, which are no longer needed to be held together by that energy, will actually weigh less. How much less? The exact amount of energy that was released. So that is a important application of it, and it's oftentimes not understood. When we talk about energy and mass, they really are measuring the same thing, and we call it energy mass equivalence. There's an equivalence between the two of them.